For decades, scientists tried to figure out what sits at Jupiter's center, and every answer fell apart because we simply couldn't see through the planet. Then Juno measured Jupiter's gravity with enough precision to finally reveal it, and the result immediately broke every leading theory. Jupiter's core does exist, but it's not solid, it's fuzzy, a huge diluted region of heavy elements spread far beyond where any core should be. However, that shouldn't be possible. Why would a planet end up with a core like that? Why would heavy elements float instead of sink? And what does this say about how the solar system actually formed? Let's take a closer look. For decades, the dominant explanation for Jupiter's origin was core accretion. In this model, Jupiter began as a growing collection of solid material, dust, icy grains, and small rocky bodies within the early solar system. Over time, these solids accumulated into a core roughly 10 times the mass of Earth. Once this core reached a critical size, its gravity became strong enough to draw in enormous amounts of hydrogen and helium from the surrounding disk. This rapid gas inflow transformed it into a gas giant. Core accretion also naturally explained one important observation. Jupiter contains more heavy elements than the Sun. A large solid core forming first would account for that enrichment. However, another model emerged as a serious alternative: gravitational collapse, also called direct collapse. In this scenario, Jupiter did not begin with a solid core. Instead, a region of the solar nebula, rich in gas, became gravitationally unstable and collapsed inward on a short timescale. The result would be a planet composed mostly of hydrogen and helium, with little or no concentrated solid core. This model matched certain Jupiter-like properties, such as its overall mass and its internal heat. But it could not easily account for Jupiter's excess heavy elements, or the fact that many disk simulations naturally produce solid planetary cores. Because Jupiter's interior could not be directly observed, the disagreement between these two formation pathways persisted for decades, with neither model able to fully resolve all of Jupiter's known properties. The first hints came from Juno's measurements of Jupiter's gravitational field. During each close pass over Jupiter, NASA's Juno spacecraft sends a continuous radio signal back to Earth. By measuring this signal extremely precisely, scientists can detect the smallest changes in Juno's speed, changes far too small to notice in real time, but easy to see in the radio data. These tiny speed shifts happen because Jupiter's gravity is not uniform. It pulls on Juno with slightly different strength depending on what lies beneath the part of the planet Juno is flying over. By mapping these speed changes across many flybys, scientists can determine how Jupiter's mass is distributed inside the planet. Regions with more mass pull a little harder on Juno. Regions with less mass pull a little less. When all of these measurements are combined, they create a detailed picture of Jupiter's internal gravity field. But Juno's measurements did not fit either of the two models. The gravity field showed patterns that were not symmetrical and not consistent with a compact core. At the same time, they were not consistent with a completely uniform interior either. Instead, the data revealed that the heavy elements inside Jupiter extend across a very large region rather than being confined to a small central area. This result surprised scientists. Before Juno, the leading theories of Jupiter's formation predicted that the heavy elements in the planet should have moved inward over time. No matter whether Jupiter formed with a core or without one, the densest material was expected to be packed tightly near the center. But Juno's measurements of Jupiter's gravity told a different story. They showed that the heavy elements are not confined to a small central region. Instead, they are spread out through a much larger zone deep inside the planet. The measurements strongly suggest that Jupiter's core is not a small solid ball, but instead extends outward, diluted, diffuse, and mixed with the surrounding metallic hydrogen. This idea became known as the fuzzy core model. In this model, Jupiter does not have a sharp dividing line between a core and the surrounding layers. Instead, the proportion of heavy elements changes gradually with depth. The deepest region contains the highest concentration, but that concentration slowly decreases as you move outward. This diffuse core likely occupies a large portion of Jupiter's total radius. much larger than a traditional, well-defined solid core would. Once scientists accepted that Jupiter has a fuzzy core, the next challenge was understanding how such a structure formed. Gas giants don't naturally blur their interiors, especially under Jupiter's extreme pressures. Something in its early history must have mixed heavy elements into a broad, diffuse region instead of allowing them to settle. Three main explanations emerged: core erosion, giant impacts, and messy formation, none mutually exclusive, and all offering insight into Jupiter's earliest conditions. The simplest idea is that Jupiter began with a compact rock ice core, as classic models assume, but that core gradually dissolved. Under normal conditions, heavy materials don't dissolve in hydrogen, but Jupiter's deep interior is anything but normal. Near the center, pressure turns hydrogen into metallic hydrogen, a conductive fluid with properties unlike anything on Earth. In this environment, materials such as iron, silicates, and magnesium oxide can break down and dissolve. In that case, convection could slowly transport dissolved material outward over long timescales. Gradually, the sharp core boundary would soften into a transition zone, a gradient of heavy elements that fades outward instead of ending abruptly. The model fits Juno's measurements well, but erosion alone raises questions. Why didn't the heavy elements resettle? Some simulations show that once mixed into metallic hydrogen, the material resists separation because convection keeps stirring it. Other models suggest that the mixing creates stabilizing gradients that suppress further sinking. Still, erosion doesn't explain everything, especially the large radial extent of Jupiter's fuzzy core. That leads to the second hypothesis. Another possibility is that Jupiter's core was disrupted by a major collision early in its formation. In the young solar system, giant impacts were not rare. Earth's moon likely formed from one. For Jupiter, the impactor could have been a planetary embryo several times Earth's mass. If such a body struck while Jupiter was still forming, the collision might have penetrated deep into the planet, stirring material and injecting heavy elements into the interior. Early simulations once showed that such a collision could spread core material outward and produce a diluted, extended core, similar to what Juno later inferred. This made the impact idea an appealing explanation for Jupiter's fuzzy core, but newer models revealed complications. While a collision can temporarily mix heavy elements, most simulations now find that much of that material would eventually sink again, reforming a more compact core. Still, the impact hypothesis isn't entirely ruled out. A collision could have contributed to Jupiter's mixed interior, especially if it happened early and under the right conditions, and it may help explain some asymmetries in Jupiter's gravity field. But on its own, a single impact is unlikely to be the sole cause of Jupiter's vast diluted core. Instead, it's now seen as one possible piece of a larger story. A third hypothesis suggests that Jupiter may never have had a clean, sharply defined core at all. Instead of forming a solid core first and then pulling in gas, Jupiter might have accumulated gas and solids at the same time. In this scenario, heavy elements don't settle into a neat rock ice center. Instead, they mix into the growing envelope from the very beginning, creating a layered interior with gradual changes in composition. Some formation simulations show that this process can naturally create density gradients, zones where heavy elements are more concentrated deep down, but gradually decrease outward. These gradients can be surprisingly stable. They act as barriers that slow down convection, helping mixed heavy materials stay suspended rather than sinking back into a compact core. If Jupiter grew this way, its fuzzy core wasn't created later. It was built in from the start. This idea has gained traction because it doesn't require a giant impact or billions of years of core erosion. It also fits with what we see beyond our solar system. Many exoplanet gas giants have densities that don't match the traditional solid core plus gas model. A diffuse gradient-rich interior, like Jupiter's, may actually be common. In that sense, Jupiter might not be an exception at all. It may be showing us how giant planets naturally form. No single process fully explains Jupiter's fuzzy core. Core erosion can blur a dense center, but not spread it as widely. Primordial layering can create a mixed interior from the start, though its long-term stability is uncertain. Giant impacts are now thought unlikely to be the main cause. The leading view is that Jupiter's interior is the result of formation and gradual evolution, not one dramatic event, but a combination of processes over time. To understand how Jupiter could develop a diffuse mixed core, we need to understand the actual physical conditions inside the planet. Deep within Jupiter, temperature and pressure reach extremes where normal chemistry and physics no longer apply. Materials behave in ways they never could on Earth. Elements that would separate here can mix there. Solids can dissolve into unfamiliar fluids. The deeper you go, the more unusual the behavior becomes. Pressure begins rising quickly, only a few hundred kilometers below the cloud tops. At the clouds, the pressure is similar to Earth's sea level. A few thousand kilometers down, it is already thousands of times greater than at Earth's surface. The increase doesn't just continue, it accelerates. Each layer compresses the next one beneath it. Near Jupiter's center, the pressure reaches tens of millions of atmospheres, enough to push matter into states it would never enter under ordinary circumstances. Hydrogen, which makes up most of Jupiter, undergoes one of the most dramatic transformations. It stops behaving like a normal gas or liquid and becomes metallic hydrogen. In this state, electrons move freely as they do in metals, allowing the material to conduct electricity and reflect light. It behaves partly like a dense liquid and partly like a metal, forming a deep, hot, and vigorously moving layer that fills most of Jupiter's interior. Metallic hydrogen is central to understanding Jupiter's diffuse core. In this form, hydrogen can dissolve heavy elements, such as iron, silicates, and rocky material, in ways that ordinary hydrogen gas cannot. Under Jupiter's immense pressures and temperatures, these elements can slowly dissolve into metallic hydrogen. The process is not fast, but over billions of years it can erode or blend material that might otherwise form a compact core. Then there is the temperature. Jupiter's interior is extremely hot, possibly over 20,000 degrees Celsius near the center, hotter than the surface of the sun. At these temperatures, atoms vibrate intensely, chemical bonds break, molecules fall apart into individual atoms. Even heavy elements can lose their usual chemical structure and become part of a high-energy mixture rather than forming separate layers. Under Jupiter's extreme conditions, heavy material doesn't simply sink in a clean, orderly way. Whether it settles or stays suspended depends on how it interacts with convection and composition gradients deep inside the planet. Metallic hydrogen, created under immense pressure, acts like a churning, electrically conductive fluid. Heat leaking from the interior drives powerful convection, launching huge currents that circulate material up and down through Jupiter's layers. If heavy elements dissolve into this metallic hydrogen, these flows can transport them outward, blurring boundaries that would otherwise separate a solid core from its surroundings. Another important effect is the presence of compositional gradients, slow, continuous changes in the concentration of heavy elements with depth. These gradients can limit convection. In some regions, mixing happens. In others, it is suppressed. This creates a broad transitional zone rather than a sharp boundary. Moving inward, layers generally become richer in heavy elements, forming a gradual transition that matches what many Juno-based models suggest. All these factors combine to make Jupiter's interior fundamentally different from anything on Earth. Solids don't stay solid. Gases don't behave like gases. Liquids behave in unfamiliar ways. Hydrogen becomes metallic. Heavy elements dissolve into it. Convection stirs materials that would normally separate, while gradients prevent complete mixing. The result is an interior shaped by competing forces, heat pushing material apart, pressure squeezing it together, convection circulating it, and gradients holding certain layers stable. In such an environment, a fuzzy, extended core is not unusual. Jupiter's magnetic field provides more evidence that its interior is not neatly layered. The planet has the strongest magnetic field in the solar system, created by the movement of metallic hydrogen deep inside. But when Juno measured the field in detail, it found that the field is not symmetrical. Jupiter's magnetic field is highly uneven, with concentrated strong regions, like the Great Blue Spot in the northern hemisphere, and broader, weaker areas elsewhere. This uneven pattern does not fit with a planet that has a compact, well-defined core. Models with a clean, sharply defined core tend to produce smoother magnetic fields, but a diffuse, mixed core does the opposite. If heavy elements are spread out and blended into the metallic hydrogen, then the fluid does not move uniformly. Some regions have more heavy material and conduct electricity differently. Other regions are dominated by metallic hydrogen and flow more easily. If heavy elements are unevenly distributed, they can affect how metallic hydrogen flows, which may help explain some of the field patterns Juno observed. This shows that Jupiter's fuzzy core directly affects how the magnetic field is generated. The unusual magnetic patches are not surface features, they are signs of uneven flow patterns deep inside the planet. In this sense, the magnetic field acts like a window into the interior, revealing how a diluted core can disrupt the motion of metallic hydrogen. Because Jupiter's magnetosphere extends millions of kilometers into space, these internal irregularities scale up into one of the largest structures in the solar system. The fuzzy core is a detail hidden at the center that influences the magnetic environment around Jupiter, including its moons and radiation belts. As evidence grew that Jupiter has a diffuse, mixed core, the consequences reached far beyond Jupiter itself. Because Jupiter is the largest planet and formed early, it has long served as the main reference for how gas giants work. Its internal structure guides how researchers interpret exoplanets, model giant planet formation, and reconstruct early solar system conditions. Juno's finding that Jupiter lacks a compact core and instead may contain a broad region where heavy elements are mixed into the surrounding material forced a major re-evaluation of these ideas. A major shift is the realization that giant planets can form in more than one simple way. Jupiter's interior indicates a formation history shaped by several processes acting together, including the buildup of solids, rapid gas capture, mixing inside the planet, and possible disturbances during growth. Small differences in timing and environment can lead to large differences in internal structure. Gas giants are now increasingly seen as products of varied and sensitive early conditions rather than a single standard formation path. This update changes how scientists interpret exoplanet data. Jupiter was previously used as the baseline for comparing the masses, sizes, and densities of distant gas giants. A fuzzy interior changes that baseline. Two planets with the same mass may have very different internal arrangements. Some exoplanets once considered unusual because they seem too inflated, too dense, or chemically unusual, may simply contain partially mixed or extended cores. This reduces the need for unusual explanations and highlights interior mixing as a common cause of observed differences. Juno's findings show that mixed or layered interiors are possible among gas giants. Many hot Jupiters show unexpectedly high heavy element content, unusual heat output, or mismatched sizes. If diffuse interiors are widespread, these traits become easier to explain. Jupiter's structure provides a physical basis for rethinking how strongly irradiated or migrating gas giants evolve below their visible atmospheres. If Jupiter's diffuse core formed partly because of a large collision, then violent early events may be more important in shaping gas giants than previously believed. Exoplanet systems already show signs of instability, tilted orbits, close-in giants, and missing outer planets. Juno's findings suggest that such events can modify deep planetary interiors, helping explain the large differences seen among giant planets. Juno changed the story of Jupiter. Its data suggest Jupiter doesn't have a sharp, solid core, but a wide, mixed region where heavy elements blend into hydrogen. That means Jupiter didn't form in a simple, orderly way, but through a complex history of growth, mixing, and slow transformation deep inside. For years, people thought the question was whether Jupiter had a core or not. Now we know the real answer is more interesting. It has something in between.